Hello, I'm Becca Ellington. I'm explaining my answers for the take-home exam. I'm going to share my screen and go through how I answered the questions as I did screen. Okay, so the first question, carbon monoxide and oxygen can be reacted on a mixed alloy catalyst to produce carbon dioxide, and the given reaction mechanism is listed. Where sites SA and SB are the sites in catalyst A and B respectively. And we have to determine the rate law, assuming that the reaction step is the limiting step. So basically the procedure I did here was I wrote out the reaction rates for each of the different steps. And then I used the pseudo steady state hypothesis that states that all of the non-rate determining or non-limiting steps are equal to 0. And then I also wrote a site balance, and I wrote a site balance for both the catalyst A and the catalyst B, which I'll kind of go through. And I did that in order to get rid of any vacant concentrations and any intermediate concentrations so that I could write my final rate law. So let's see, over here, you'll see that I have my reaction 1, my reaction 2, reaction 3, reaction 4. The first two reactions are adsorptions. One of them onto the A catalyst, one of them onto the B catalyst. The third step is the reaction step, so I did not set it equal to 0. And then the fourth step is the desorption step. Setting them all to 0, I was able to get concentrations for different molecules at the different sites. And then plugging it into the site balance, as I said earlier, there's the site balance for the A catalyst and the B catalyst. And then I just plugged in what I had solved for before. And so basically what we have is 6 unknowns and 6 reactions, or 5 unknowns and 5 equations. And then you plug you solve for all the unknowns and you plug them into the final reaction rate, which is going to be equal to the reaction rate of the limiting step. So I solved for each of the concentrations, solved for the vacant concentrations, and then plugged them all into the final reaction. That's what I got as my final number. For question 2, a cylindrical pore, part of it is poisoned. And so for the poison section, I did a regular shell balance for the mole flux. And no reaction is taking place in this section, so then it ends up just being that the mole flux is constant. And then I plugged in Fick's law and solved for the concentration of Ca. And for my integration constants, or I used the boundary conditions, which stated that at the very beginning at C equals 0, the concentration of A is equal to Ca site. And then at C equals 2/3 of L, or 8 millimeters, that is equal to C1. And I stated it was Ca1 because I was getting confused with the integration constant and with the concentration constant. So plugging that in, I got my profile for Ca for the poisoned region. I got it, and then I plugged in the numerical answer where everything is in terms of centimeters. For part B, it says if the regular effectiveness factor for no poisoning is equal to that, calculate the new effectiveness factor. And so I started with the beginning of the derivation of the effectiveness factor, which is the actual rate over the ideal rate. I said that the system is a 2/3 poison system, so the ideal rate would still consider that. And then had to split the integral for the actual rate into the poison section and the reactive section. I derived a concentration profile for the reactive section, took the two integrals and plugged that back into eta to get my final expression for the effectiveness factor. Going into question 3, it was an endothermic reaction with an elementary rate law and a PBR, with the weight of the catalyst is 50 kilograms. And we had to find, initially when no inert is present, a conversion temperature and pressure profile. So I'm going to go through how I derived those different profiles, and those are all with respect to the weight of the catalyst. So I essentially have a dxdw, dtdw, and a dpdw. So I derived the concentration based on the design equation by plugging in a gas phase concentration into the rate law equation, and by saying that X or that FA is equal to FA naught times X. This is my conversion profile. For the temperature profile, I took the energy balance, considering that there was no work and no heat done in the reaction, and the delta Cp was negligible. I rearranged it and then took the derivative of T with respect to W and got this final reaction in terms of X, delta Rx, and then the Cp, the summation of the theta Cp, which is just equal to this because a lot of the thetas equal 0. Units checked out, I used the Ergun equation for the pressure drop, pretty simple. I didn't derive an equation for Ft, so I replaced it with 1 plus epsilon X. And then I put the code into MATLAB and took so you'll see my differentials here, my conversion equation, my pressure drop equation, and my temperature equation. And then this is for part B. And then I just plotted each of those after running ODE 45 on them. For part B, it's pretty similar. It's you have to find the conversion at the end of the tube when you're changing f of I. So I created another differential for theta I, not f of I, my bad. So I could kind of explain it in my code. That's a little bit easier. So I had a theta I that I was changing based on basically, theta I is the same throughout. So whatever I change the boundary condition to, the initial condition is what theta I is going to be. And then I run the ODE and find what the very last value in the array is for the conversion. And then I was able to plot, how theta changes with the conversion. We were able to see that it changes and that there is a maximum reached. And that was due to the fact that if you're looking at the energy balance, as you increase theta I, then X is going to increase. And that happens until a point where the theta I is increasing so much that it's actually affected the rate of the reaction because there's not enough A in the initial concentration. And that's essentially my code, my whole project. Thank you.